Okay, so this is 14.2 and 14.3. I'm going to do both of these sections together because they fit very well together. 14.2 is about the calculus of vector value functions, and 14.3 is basically an application of that motion, which we've basically been thinking of as the primary application of vector value functions. So derivatives, integrals. All right, so we'll do them both together. So the good news is we have a vector value function equals whatever, x of t, y of t, z of t, right, in space, let's say. The good news is the derivative is super simple. So what do? You just take each of the pieces individually, take their derivatives, x prime, y prime, z prime. All right, so basically working with the calculus, or at least at this moment, working with the calculus of one variable of vector value functions is essentially doing three single variable calculus problems, right? You work with x of t, get x prime of t, y of t, y prime of t, z prime of t. Okay, so it's just triple the amount of work. Nothing too weird or strange going on in terms of the basic calculations. Of course, I've written an example in space. If you only had a vector value function in a plane, just cover up the z part, and you're all set there. Okay, notation. R prime of t, that works pretty well. We also have dr dt. Usually we use the straight d's because we're not doing partial differentiation. Our thing is only a function of one variable. If you want to evaluate the derivative at a particular location, right, t equals 3, something like that. All right. Or of course in the other notation, r prime at 3. Okay, so the mechanics of taking derivatives is very, very straightforward. Let me just do one example. R of t equals our favorite vector value function. So again, this is motion counterclockwise around a circle. R prime of t is just going to be the derivative of cosine is minus sine, and then comma, the derivative of sine is cosine. And that's it. You're all set. All right. Okay. Technically, we probably should do a discussion about limits, all that kind of business, but I think this is good enough. For the purposes of our class, this is good enough. We'll just say that as long as you can take the derivatives of the individual pieces, you're going to be okay. All right. Okay. Let's interpret what this derivative means. And we'll kind of see the limit interpretation anyway from that, but we're not going to do it, very, very formally or anything like that. Okay, so interpretation. Let me draw. So let's say we have a r of t, and just for convenience, I'm going to assume it's a vector value function in the plane, just so I can draw pictures. But everything goes exactly the same for space. Okay, so let me draw time on this side. And let me draw the curve in the plane on the other side right here. All right, so let's say here's my curve. Okay, let's say we're interested in what's going on at time t. We're basically interested in what the the derivative means. So what I'm going to do is, just like in one variable calculus, I'm going to consider r at the time of interest, r at t, but also at t plus delta t. All right, where delta t is small, just like in one variable calculus. Okay, so basically the same idea. And essentially, r prime of t, right, is going to be the limit delta t goes to 0 of r of t plus delta t minus r of t over delta t. All right, exactly the same formula that you saw in one variable calculus, except now, of course, everything is vector valued. Okay. Again, I don't want to go into what a limit is and all that kind of business. I'm just going to look at kind of this inside quantity here and see how it relates to the picture of what's going on. Okay, and then we'll look at what happens when delta t goes to 0, and we'll get a very nice interpretation of the derivative. Okay, so let's say in our picture when we're at t, right? Let's say r of t is equal to that value right there. All right, so this guy here is r of t, right? And let's say at t plus delta t, we are right there. Oops. R of t plus delta t. All right. Okay. So what is the quantity? This difference quotient in here. What does this quantity represent? Well, if you think about this in terms of vectors, we have r of t plus delta t is this vector right there, right? R of t is that vector right there. If you subtract them, you're going to get this vector right there. All right. Okay. So this is the interesting vector. This is r of t plus delta t minus r of t. Okay. Let me do something like that. All right. Now, what happens? Let's just concentrate on the top part of this difference quotient. So what happens as delta t gets smaller and smaller and smaller? Well, we can see maybe something like this. Let me draw another picture down here just because it's getting a little messy. So here's t, and I'm going to zoom into this area. Sorry, this area over here. Here's r of t. Right? Now, if I put in t plus delta t, right, being right there, I'm going to get the difference, r of t plus delta t minus r of t, to be something like this. All right? Now, if I pick a closer one, right, so this is r of t plus delta t, right, our initial one, right, t plus delta t. Now, if I pick a closer one, right, basically an even smaller time interval after t, I might end up here. Right? So my arrow would be that. My vector would be that, the difference. Okay? If I pick one even smaller, maybe I'm here. Right? If I pick one smaller, maybe I'm here. Okay? So what you can see is exactly the same thing you saw in one variable calculus. These vectors are getting closer and closer and closer to looking like it's tangent at r of t. So again, let me do another kind of zoomed in view. Something like this, something like this, something like this, something like this. And as these vectors, right, as the remember in one variable calculus you would have called these secant lines. As these secant lines, as the second point gets closer and closer and closer to my base point, I'm getting closer and closer and closer. The arrows are getting closer and closer and closer to this guy right there. All right, that guy being tangent to my curve. Okay, and again, tangent, same idea as tangent from one variable calculus, right? Where you kind of basically just think of it as this arrow is just touching my point, just touching my curve at the point of interest. Okay, so this argument tells me that r prime of t, the direction is tangent to the curve. Okay. All right, and not only that, you can see that if as we move from t, as t gets bigger and bigger, right, t to t plus delta t, in the picture I have at least, we're moving in this direction along the curve, right? And so the arrow right there actually indicates the direction of motion. Okay, so points in direction of motion. All right. Okay, so that's the kind of idea behind what the difference is up here. Okay. Now, of course, we want to divide by this delta t, because if we don't, the arrows are just going to get smaller and smaller and smaller, right? And as delta t gets smaller and smaller and smaller, and the arrows are just going to go to zero, right? The length of them is just going to go to zero. So that's kind of one way to think of perhaps a reason why we might want to put a delta t. I'm going to have another one in just 1 second. Okay, in any case, in terms of the picture, what's going on is, or in terms of, let's say, motion, the arrow being tangent to the curve, you can think of it like if you're driving along this road and suddenly you hit a patch of ice right there, right? Let's say you're driving this way along the road from left to right. And you hit a patch right there, you're going to continue, right? If you're driving like this, you hit a patch of ice, you're going to continue going straight this way, right? If you've lost traction with respect to the road, then you're going to continue this way. You're just going to slide in this direction. And what is that direction? It's the tangent direction. Okay, so that's what the direction of the r prime represents. Okay, and same thing perhaps over here. If you're driving all the way to here, you hit a patch of ice, you're going to start to slide in this direction, right? And again, that's tangent. That direction is tangent to the direction of the curve. Tangent to the curve. All right, so it gives you your direction of motion, essentially. All right, but what about, so that was the directional aspect of the derivative. What about the length aspect? Well, again, let's look at our difference quotient. Oops, I don't want to put equals, but again, the length of this guy is going to be a limit, right, of the length of the difference quotients. So let's just take a look at the difference quotients. So it was r of t plus delta t minus r of t over delta t, right? Length of that. Okay. So these two guys are, of course, related. When delta t goes to 0, you're getting closer and closer to that guy, to r prime of t, basically by definition. All right, but what is this thing on the right-hand side? This is, if you look at this delta t, that's a, let's just assume delta t is positive. Of course, everything works if it's negative, but just for convenience, right? This is going to be r t plus delta t minus r t, absolute value like this, and then just divided by the number delta t. All right. Okay, now the guy on top, super simple interpretation. Again, we draw our picture. Here's r of t. Here's r of t plus delta t. All right. Let's put the origin right there. So we're doing that. We're doing that. And then we're subtracting. We're ending up with that. And so what we have is roughly the distance that we moved, right? Not exactly, because we actually moved in a curved distance, a curved manner, but roughly the distance that we moved from time t to time t plus delta t. All right. So this is roughly going to be distance traveled, right? From t to t plus delta t. All right. And then we're dividing by that delta t. Okay. And again, it's important to say roughly because this is a straight line calculation, whereas that guy's curved. But when delta t gets smaller and smaller and smaller, right, the curves generally, right, for nice functions are going to get, in a way, straighter and straighter and straighter. So this distance, this approximation here gets better and better and better. All right. Okay, in any case, what is this thing on the right-hand side? This is basically your speed, right? How far you traveled divided by how long it took, that's your speed, right? If I traveled 100 miles and it took me 2 hours, my speed is 50 miles an hour, right? I mean, technically, I should say average speed, something like that, but you get the picture, okay? So the right-hand side, as delta t goes to 0, represents or goes to your velocity, your instantaneous velocity. And again, this is basically exactly the same idea in one variable calculus, where the slopes of the secant lines, right, go towards the instantaneous rate of change of your function. Okay. All right. So this guy here, r prime of t, the length of it is your velocity at time t. Oh, sorry, the length of it is your, is your speed at time t. All right. So altogether, length and direction are prime of t as a vector, right? It points in a direction of motion. Its length is your speed. So altogether, that would be what we call your velocity. All right. So velocity is the correct way to think of it. It's a vector. It's especially when you're talking about moving in space or in the plane in the plane. It's a vector that points in a direction of motion. Its length is how fast you're moving. Okay. All right. So that's a super important kind of feature of vector valued functions, in that it directly correlates with the concept of motion. All right. Let's see. Okay. Tangent vectors. So if you do have a curve represented parameterized by an R of t, right? Very frequently in the future, we're going to be wanting to find tangent vectors. Vectors tangent to our curve, right? So if we're here, we want that vector. If we're here, we want that vector, or the other direction, right? Whatever. That would be fine. We just don't want something, we don't want that, right? We want vectors tangent to the curve. Okay. So if we do have a parameterization, we have a tangent vector instantaneously, right? R prime of t, just from our discussion that we just had, is tangent to the curve. Okay. All right. So this is just a kind of mathematical version of what we talked about in terms of position and speed. All right. So that's not that interesting or new, but what about this? Unit tangent vectors. So oftentimes we're going to have a curve, and we're going to want tangent vectors, but not tangent vectors of crazy lengths. We want tangent vectors that have exactly length 1, right? Because for a lot of things, it's going to make our lives easier. Because once we make it a unit vector, we're kind of removing the kind of change in velocity in terms of this motion, right? So how do you find a unit tangent vector? Well, it's super simple. You just take the tangent vector that you found, right? So if t goes to this point and you want the unit vector, well, r prime of t is tangent to this to the curve, but it might be the wrong length. So what do? You just divide by its length. Okay, so this is unit tangent. All right, and if you need the one, if this happens to be in the direction opposite of the direction you need, you can just put a minus sign in front. All right. Okay, so unit tangent vectors, super useful for us in the future. Okay. Again, all of this, of course, depends heavily on the fact that you can find a parameterization of your curve, or you have a parameterization of your curve. All right, for our kind of typical example of r of t equals cos t, comma sine t, right? We said r prime of t was minus sine t cos t, right? And this example is really nice because it just happens that r prime of t, the length of it is going to be sine squared cosine squared. It's going to be 1. All right. So this kind of motion around a circle is actually very special, because it's always, you're driving around a circle at a velocity of 1. All right. Or sorry, at a speed of 1. Right. A constant at a constant speed. Okay. Let me actually. So I promised that r prime is tangent to the circle. Let's see, is that actually true? Let's just check it, let's say for t equals 0, right? At t equals 0, my position is right there. Is r prime at 0 tangent to that? Let's see, r prime of 0 is minus sine of 0, which is 0, and then cosine of 0, which is 1. So the tangent vector r prime at 0 is exactly that, right? So it looks good, at least for that particular example. Okay. Let's see, for the circle though, the circle is really special in that I can actually confirm that it works at every other point very easily, right? Because I can just take the dot product, r of t, dot r prime of t, right? And because this is the circle, r of t always points like this, right? Directly from the origin to the circle. And my tangent vector should be exactly like that, right? So r of t dot r prime of t, if I look at these two guys, cosine times the negative sine, I get minus cosine times sine. And then plus sine t, cosine t, I get 0. Right? So this is kind of the correct picture. Okay, so it's kind of special in that position is always perpendicular to your velocity for circular motion. All right. Okay. Or at least, for circular motion in general. And we know this is true actually, because if you are in circular motion, let's say even radius r, or let me do radius capital R, then we know that r of t, the length squared, let's say, just to make things a little simpler, is r squared, right? But what is the length squared? That's r of t dot r of t, right? That's equal to r squared, right? And then what I can do is I can take the derivative of both sides, and I'm going to get 0, so d dt, both sides. Now I'm going to get 0 on the right-hand side, because that's just a number r. And what's going to happen on the left-hand side? Well, we're going to get r prime of t, and then we'll talk about this actually formally in 1 second, dot r of t plus r of t dot r prime of t. All right, product rule. This guy is 2 r of t, r prime of t. And again, that's equal to 0. And so r of t is always perpendicular to r prime of t when you're moving in circular motion, right? No matter what parameterization I'm doing, as long as I'm moving in circular motion. So I could be speeding up, I could be slowing down, doesn't matter. Okay. Now, going from here to here, from this step to that step, does that actually work? Right? What are actually the rules of the interaction between ddt and dot products? Well, I assumed in this calculation that the product rule basically, the product rule basically works. And that's what the next topic is actually about. So rules of differentiation. And basically the idea is that, yes, the product rule does work. And so this calculation is completely valid. All right. So rules of differentiation, first thing I want to say is they're all expected. All right. So there's nothing unexpected going on here. Everything is as you would have hoped. All right. So for example, ddt of, if your vector valued function is always just a constant vector, right? ddt of that is 0. And again, all of these come directly from the fact that when you take the derivative of a vector valued function, you're taking the derivative of each piece, each entry, x, y, and z entries separately. All right. Okay, so basically this first one is true because when you take the derivative of the x component, you're going to get 0. The y component, you're going to get 0. Z component, you're going to get 0 because they're all constants. All right, so it's all boils down to one variable calculus. Okay, ddt of u plus v is, again, boils down to one variable calculus, ddt of u plus ddt of v. Okay, nothing fancy going on there. Okay, the next one is kind of interesting. ddt of f of t times u of t. All right. So instead of just a simple constant, now we have a function of t. All right. But the interesting thing here is that this thing on the left is if you fix a t, right? If t is fixed, that's just a scalar. right? And then this guy's a vector. So this product, f of t times u of t, this is actually scalar multiplication of a scalar times a vector, all right? So it's not just regular multiplication, at least the way it's written here, okay? All right, in any case, what is it? Product rule, right? That's what you would expect. When you see the product of two things and you're taking the derivative, your expectation is that something like the product rule should be true. And in fact, it is. So this is just f prime of t, right? Just a regular f prime of t of a one variable function, u of t, and then plus f of t, u prime of t. Okay. All right. Next one. Let me actually put all the product rules together. So what does that mean? Well, there's a couple other product rules, right? We have another type of product, the dot product, and we just talked about this. And let me emphasize of t, v of t, right? And it works out exactly like we said above, as we expect. So u prime of t, v of t, plus u of t, v prime of t. And this over here is the dot product, dot product, dot product. All right. And there's an arrow here. Okay. So it's exactly what we would expect in terms of the product rule. But notice that maybe this expression isn't as completely simplistic as it might appear on the surface. Because what's happening on the left-hand side here is this guy right here, dot product, is a function, right? When you dot two vectors, you get a number. So if you dot two vector-valued functions, you're going to get a regular one-variable calculus function. So this derivative on the left-hand side is actually a one-variable calculus derivative of a regular one-variable function. Okay. Whereas down here, this derivative is a vector-valued function derivative, right? The v prime is a vector-valued function derivative, right? So you're ending up with a vector-valued function as the u prime, dot a vector-valued function v, and then on the other side of the sum, you have a vector-valued function u, dot vector-valued function u prime. Okay. So the derivatives on each side of this equation are actually slightly different. Again, the one on the left-hand side is just a one variable calculus derivative, whereas the right-hand side derivatives are actually vector value function derivatives. Okay. All right. That just makes the equation a little bit more interesting than it might appear. All right. And we have another type of product. We have the cross product. And does that work out? Yes. So this is u of t, u prime of t, cross v of t, plus u of t cross v prime of t, right? And again, the product rule, right? Take the derivative of one, leave the other. Take the derivative of the other, leave the first one. Okay. And again, we can see all the three different products that we could have, they all work out in terms of the product rule. All right. Okay. Why are all these true? You can just write out, and it'll just pop right out. For example, if u of t, right? If you write u of t as x1 of t, comma y1 of t. Let's just say we're in a plane, and v of t were x2 of t, y2 of t. Then its dot product is going to be x1, x2 plus y1, y2, right? And then you just take the derivative of that using the regular product rule, and then you can just check it against the right-hand side, and everything will just pop out and work perfectly, okay? For the cross product, if you want to confirm it yourself, write everything in terms of ijk, and then again, you know I cross j is k, k cross j is I, and so on. You can use that. Everything will pop out. All right. So I'm not going to do the computations. They work out extremely in a very, very straightforward, in extremely straightforward manner. Okay. And again, they all work out exactly how you would expect. Okay. So those are my three product rules. There's one more rule, ddt. u of f of t, right? So this is a situation where you've put a function inside another function, right? So this is going to be the chain rule, right? This is a composition. You're doing f of t, you're taking t, the variable, you're applying f to it, and then you're applying u to the result of that. So that's exactly a chain rule situation. And the chain rule works exactly like you would expect. So this is u prime of f of t, f prime of t, all right? And again, everything makes sense. This thing on the right-hand side, the first term is a vector-valued function. The second term is just a regular function. So if we fix a t, for example, t equals 0, the guy on the left is just a vector, and the guy on the right is just a number. And so this product here is perfectly legit as a scalar multiplication. Okay. All right. So this is the chain rule, of course. And we'll be using this in a very important way in the next section. Okay, notice, by the way, just a small note. Notice that we don't have a chain rule that looks something like this, right? F of u of t, because that doesn't make sense. If f is just a single variable function, it doesn't take in a vector as an input, all right? So something like that doesn't make sense. And we can't have something like this either, v of u of t, because u of t is a vector, and our vector valued functions take only numbers, right? T as input. So this expression inside the dt doesn't even make sense. Okay, so that's why we only have this single version of the chain rule for the derivatives of vector valued functions. Okay, let's take more derivatives. So we had r of t, right? We had r prime of t, and this was our velocity, right? And again, this is if we're thinking about r of t as our position, which we pretty much always do, right? Always consider vector value functions in terms of motion, right? Because we have a lot of good intuition about motion, and so that ports over to a lot of good intuition about vector valued functions. Okay. All right. Now we remember from single variable calculus, if you take another derivative, right, then you get acceleration. And that works exactly the same in the vector valued function setting. All right. So if you take the second derivative, which is perfectly legit because r prime is itself a vector valued function, if you started with a vector valued function. And so you can legally take its derivative and get a third vector valued function, and that is the acceleration. Okay, and the acceleration is the change in the velocity, right? Just as the velocity is the change in the position. Okay. All right, and you can actually see that, right? For example, technically, to take this derivative from the velocity to the acceleration, you would take r prime of t plus delta t. You would subtract r prime of t, and then you divide by delta t, and you look at this type of quantity, right, as delta t goes to 0. Well, what is that? Let me draw a curve. So let's say r of t is here, then r prime of t, let's say, is this arrow right there, right? So let's say this is r prime of t. Again, it has to be tangent to the curve. Let's say r of t plus delta t lives right there, and then so this would be r prime of t plus delta t. Okay. All right. So what happened? As we move from this point to that point, our velocity changed from this direction to that direction, right? R prime of t to r prime of t plus delta t. Okay. So this difference up here is going to be, let me do it like this. This difference up here is going to be that vector, right? It's the difference between the two velocities, all right? And what you can see is if you take closer and closer differences, then what you're getting is kind of the pull of the you're getting to see how the velocity vector is being pulled away from the natural direction that it's already going in. All right. So here we have, so just in this example here, right, we had our velocity vector starting out in this direction. It ended up in this direction, right? What happened? Well, there was some sort of pulling, some sort of force pulling our particle or whatever it is, right, kind of in that direction. Okay, so that's the idea. And so that pull is the acceleration. Okay, and oftentimes that pull is roughly going to be the force that's acting on your particle, right? Which makes sense because if you have no forces acting on a particle that's moving, right, it's just going to continue moving in this direction forever, right? Continue moving in a straight line with a constant velocity. But if you introduce some sort of pull, right, it's going to make it curve, right? Oops, I guess I've been doing the pulls in red. It's going to make it curve, right? And that's what causes non-linear motion. Okay, so you're having something act on your. You can think of it as something changing your velocity vector. Okay, and of course, if you want, you can always take more derivatives, but the interpretations of those aren't as maybe accessible as position versus velocity versus acceleration. Okay, let's again look at our favorite example. R of t equals cos t sine t, right? In this case, r prime of t is going to be equal to minus sine t cos t, and r prime prime of t is going to be minus cos t minus sine t, which is actually just negative of cos t sine t. And that makes perfect sense because, again, if your position is here, first of all, your velocity is there, tangent. And what's keeping this particle from moving in a circular motion? Well, it's the acceleration that's changing the velocity. And it's always pulling this guy towards the center. Okay. All right. Okay, so this is, I mean, the examples I've done are for very simple circular motion, but obviously you can do, r of t equals anything, right? t squared. That's a nice, interesting example. And again, everything I've talked about applies when you go into 3D motion. Sine t, e to the t, t plus 1 over t squared minus plus 1, let's say. Okay, so this would describe the motion of some particle moving in space. Now you can figure out its velocity. You can figure out its acceleration at any time very easily, just using knowledge from one variable calculus. Okay, so again, everything is working out extremely smoothly for vector valued functions. We'll see that things will be a little different when we start talking about multivariable functions in the next chapter. But for now, things are very, very nice. Okay. What about the other direction? Integration. So just as with differentiation, integration works out exactly in the same way. Right? So if you want to integrate a vector valued function, you just integrate each individual piece. All right. So if you want to integrate r of t dt, where r of t is whatever, t 1 cos t, right? So that would just be the vector valued function that you would get when you integrate t, you integrate 1, you integrate cos t. All right, so we would get 1/2 t squared, comma t, comma sine t. And then just as with one variable calculus, you better remember your constants. Let me just call them C1, C2, C3. All right. Okay, and if you wanted to do definite integrals, right, integral from whatever, 1 to 3, then this would be 1 to 3 here, 1 to 3 there, 1 to 3 there. Literally nothing very exciting. Okay. All right. In terms of applications, we have exactly the same application that we had in one variable calculus when we thought about motion, right? If I have a of t described as a vector valued function, that means I can capture v of t by integration, right? And that means I can capture my position, r of t. What's going on here? R of t by another integral. All right. So I integrate. Just like in one variable calculus. Exactly the same idea. All right. Of course, things are a little more complicated because, for example, if we're talking about, let's say, gravity, right? Let's say in space, so three-dimensional gravity, where the acceleration of the Earth is pulling you straight downwards along the z-axis. So let's say we're only talking about motion in a small, very, very close to the surface of the Earth, right? Then this would be, for example, 0, 0, minus whatever, 32 feet per second, 9.8 meters per 32 feet per second squared, or minus 98 meters per second squared. Okay, so when you integrate, you're going to get exactly what you would expect. All right, you're going to get exactly what you expect. Sorry, I stopped the recording by accident. Hopefully I can stitch these two together. So you're going to get exactly what you expect. You integrate here, you get a constant. I think our book likes to use, let me try to keep consistent with the book's notation. X, here we go. So U0, V0, minus 32t plus W0, right? So that's going to be my velocity. Okay, and of course, U0, V0, W0 is going to be my initial velocity, right? And again, you can compare this with just single variable calculus. If we're doing simple, again, projectile motion, then we get V of t is minus 32t plus V0, right? And of course, x of t, our position would be minus 16t squared plus V0t plus our initial position, right? So in exactly the same way, if we integrate again, we're going to get U0t plus x0, V0t plus y0, and then comma minus 16t squared plus W0 of t plus z0. All right. And again, just as in single variable calculus, the x0 represent your initial position. Now x0, y0, z0 represents your initial position. Okay, so you can do exactly the same kinds of mini physics problems that you did in single variable calculus, right? So if you're throwing a ball off a 100-story building, you've thrown it upwards at a velocity of 10 feet per second, right? How long does it take the ball to hit the ground, right? So in that case, you're trying to figure out when is x of t equal to 0. So all the information that I gave you, right? You're throwing from a 100-story building. You're throwing upwards with some initial velocity. That gives you v0. That gives you x0. And so now all you have to do is solve a quadratic equation to get when the ball hits the ground, right? When this guy is equal to 0. So in this new setting, right, in space, again with projectile motion, simple projectile motion, same exact idea, right? If I give you where I was initially, right, maybe at 1, 2, 100, right, if I'm on top of a 10-story building, and I'm throwing this rock or this ball in a certain direction, right? The direction 5, 7, 6, right? With the velocity being the length of that vector, then I can figure out how far this ball is going to travel before it hits the ground. I can figure out what its maximum height is going to be. All the same ideas, right? Except, of course, things are more complicated because you have three entries instead of just one. But of course, we're doing much more interesting kind of motion, right? With single variable calculus, it's kind of lame in that you're just talking about throwing a ball up and then it comes back down and hits the ground. But now we can talk about actual physical real life motion where I'm maybe throwing the ball in that direction, right? From a certain height where this is the shadow, right? And the ball is going to fly in this direction and hit the ground somewhere down here, right? So you're describing actual 3D motion under 3D projectile motion under the force of gravity on Earth. Okay, so where does it hit the ground? Well, that's going to be when z equals 0. Z of t equals 0, right? Again, where I've written r of t as x of t, y of t, z of t. Right, so you'll see a problem on this on the homework, right? They'll ask when does the ball hit the ground? It's when z of t equals 0, right? What is the maximum height of the ball? That's the maximum z, right? So you want to find the maximum z coordinate, all right? Okay, how far? Here's a good one. I think you'll see this on the homework as well. The range. So our book calls it the range. Yeah, the range of this projectile. So that would be that would just be how far it moved in the xy direction. Okay, so if you're starting out right here at the in this example at the origin, let's say, so the range would be that distance right there. Okay, just your final position minus your initial position in terms of just the xy distance. All right. Okay. So pretty useful in terms of real life applications, but kind of unsatisfactory at the moment in terms of the kind of techniques we have for studying curves, because what we see is if you give me a random curve like this, right, and you parameterize it, r of t, your parameterization could be very different from somebody else's parameterization, right? So maybe your parameterization looks like this, where let's say here's t equals 0, t equals 1, and maybe you're slowing down, t equals 2, t equals 3, maybe you've sped up, t equals 4, maybe you've slowed down again, and then maybe you're going at a constant rate here, t equals 5, 6, 7, and so on, right? But maybe somebody else is going to give me a parameterization where, let's say we even start at the same point, but perhaps they go slower, right? So there t equals 1, t equals 2, t equals 3, and then maybe they speed up like that, right? So you're going to have two different descriptions of the same curve. And of course, you're always going to, if you want to study that curve itself, not necessarily the motion along the curve, right? In other words, if you want to study the properties of the road instead of necessarily the properties of how cars are moving along the road, then all these different parameterizations give you a lot of complications because they're giving you extra information that you kind of don't really want, right? You don't care about the car speeding up or slowing down. You actually care about the road. Okay, so what 14.5 is about is finding kind of a standardized parameterization that allows us to, in a way, just study the road, right? So we're kind of throwing away information about the motion of the cars on the road, okay? And that's going to be called arc length parameterization. So we'll do that in the next video, and that allows us to study curves as long as you have such a parameterization, study curves very, very easily in a way. Unfortunately, the disadvantage is that arc length parameterizations are not necessarily that easy to find if you have a concrete formula for a R of t, okay, or if you have a non-simple curve. Okay, so that'll be the last video for this week.